Hello, my name is Alex Curry. I'm a graduate research assistant at the University of Louisville, which is in Louisville, Kentucky, and I'm currently pursuing a master's degree in electrical engineering. Today I'll be presenting our conference paper demonstrating a new ink material for aerosol jet printing conductive traces and custom strain gauges on flexible surfaces that I worked on along with Dilan Ratnayake and Kevin Walsh. So I'd like to start off by giving a little bit of a background about aerosol jet printing. Aerosol jet printing is a non-contact printing process that is capable of printing a wide range of materials, including metals. These systems work by atomizing a solution of material and forming a dense aerosol mist that is then deposited onto a substrate. These systems can use pneumatic or ultrasonic atomizers, but in our case we have an ultrasonic atomizer. For the ultrasonic atomizer, ink is submerged in a bath of water with a transducer located underneath that excites the particles and causes them to break away from the ink. And since the system is pressurized, these particles make their way to the nozzle and are focused by a nitrogen gas sheath, as shown in the figure on the left. Now, the sheath of nitrogen serves two purposes. One is to focus the beam. Focusing the beam allows you to change the width of the printed traces. And the second purpose it serves is to prevent material from adhering to the nozzle. Without this, your nozzle would get clogged with the material very quickly. So the ink that we use for our experiments is a silver ink. It's manufactured by NovaCentrix. The part number is JS-A426. This ink has silver nanoparticles under 50 nanometers in size, and it has a viscosity of about 6 to 10 centipoise, which is perfect for the ultrasonic atomizer, because the ultrasonic atomizer requires inks to have a very low viscosity, typically below 10 centipoise. Now, if your ink doesn't have viscosity that low, you can dilute it to get within the desired range, but obviously this is limited based on how high the viscosity is. So on the right, you can see what these printed silver lines look like under a microscope. The line pictured is about 50 to 70 microns in width, not including the overspray, and that's about the same width as a human hair, just to put it in perspective. So before printing, we designed our strain gauge based off a reasonable line thickness of 50 microns, which we have achieved repeatedly in previous tests. We also knew that the thickness of our traces that we've measured before have been 1.45 microns, and we know that the average conductivity of our silver traces is going to be about 7 times 10 to the 6th, although that can vary based on post-processing methods. By using these values, we can use the equation at the top here to estimate the resistance we will get depending on the length that we choose. So using the width of the traces as well as the thickness of the traces, we can calculate the cross-sectional area A, and using the conductivity, we can calculate the resistivity rho of the material. And then based on those, we can choose a total length of traces to give us a desired resistance. And so on the right, you can see the design we came up with to achieve a desired resistance of about 110 ohms. So to achieve these 50 micron line widths, these are the following printing parameters that we used with this NovaCentrix ink. So the printer that we have is an Optomec decathlon print engine. We have the ultrasonic atomizer, although you can also purchase a pneumatic atomizer for it. We use a nozzle diameter of 300 microns, and we use a nitrogen sheath flow rate of 135 SCCM, as well as an atomizer flow rate of 15 SCCM. The atomizer flow rate and the sheath flow rate are the two most important parameters. The sheath being, like we discussed earlier, focusing the beam, as well as the atomizer flow rate determining how much material is actually coming out of the nozzle. Using these parameters, we also printed at a speed of 10 millimeters per second. And we also diluted our ink just a little bit with a 2-to-1 ratio of ink to deionized water for a total volume of about 4.5 milliliters of ink solution. And so pictured on the right is what the printed strain gauge looks like. So after printing, we cure the strain gauge for 24 hours using an oven at 200 degrees Celsius. Now this removes any remaining solvent, as well as it allows the nanoparticles to expand and fuse together, which in turn increases the conductivity of your traces. Now other post-processing methods can be used, but we are very familiar with the oven because we've characterized it before, and so we knew that using the oven would give us the desired conductivity values that we were looking for. To characterize the strain gauge, we need to measure its gauge factor, which is a measure of how sensitive the gauge is to a change in strain. Basically, as deflection is applied to the gauge, its resistance is going to change, and once the amount of change in resistance is known, strain gauges can be used to determine the amount of external force that's being placed on an object. So we used a basic testing setup, which is shown below, where we have the strain gauge on the left placed on a steel beam, the steel beam being this black bar, and we apply a force on the end of the beam to create deflection. Now we can measure the change in resistance, and we know the initial resistance, but we need to figure out what the strain is before we can calculate the gauge factor. So to determine the strain, we can calculate the theoretical strain based on the testing setup. So as shown below, we can use D for the amount of deflection. We can measure L1, which is the length from the end of the beam to the strain gauge, as well as L2, which is the total length of the beam. And we can measure T, the thickness of the beam, to calculate a theoretical strain based on each deflection value. The other method that we can use is we can use a commercial strain gauge with a known gauge factor, and we can measure its change resistance as we apply deflection to calculate the strain at each deflection value. So on the left here, we have a close-up picture of our setup. On the top, we have a commercial metal foil strain gauge that we used as a reference, and in the bottom, we have the strain gauge that we printed onto a Kapton sheet. And on the right, we have a zoomed out picture of the test setup with our steel beam, our strain gauge on the left hand side, as well as a micrometer on the right hand side that is applying a force with a known deflection distance on the right side. So we began by measuring the change in resistance of the metal foil strain gauge at each deflection value and calculating the experimental strain as shown in the table here. Now we knew the initial resistance of the metal foil strain gauge. We measured to be 351 ohms, and from the manufacturer we know it has a gauge factor of about 2.145. So using all these values, we can use the equation from earlier to calculate the experimental strain. And we compared that with the theoretical strain from the equation that uses the length of the beam, as well as the distance at the end of the beam to the strain gauge. And we compared these values, and as you can see, they're very similar. Some of them are even equal at specific deflection values. So using these strain values, we then measured the change in resistance of the printed strain gauge at the exact same deflection distances. So our printed strain gauge had a measured resistance of 116 ohms. And then after measuring the change in resistance at each deflection value and using the known strain values, we were able to graph each data point and come up with a line to fit the curve. And that gave us an average gauge factor of about 1.85. So in conclusion, a silver ink JS-A426 from NovaCentrix was investigated and was used successfully to aerosol jet print a strain gauge. A printing recipe was developed to be used with this ink specifically to achieve consistent 50 micron wide traces with an ultrasonic atomizer. A strain gauge was successfully printed to demonstrate an application of aerosol jet printing, and our strain gauge was determined to have a gauge factor of 1.85, making it a close competitor to commercial strain gauges. Now on top of that, a printed strain gauge has a couple advantages. One advantage is that it's able to be fabricated in under a minute once the printer is set up. Another advantage is that you can print it directly onto the device without the need of adhesive. For our future work, we plan to continue characterizing this NovaCentrix silver ink. We would like to explore other post-processing methods, including intense pulse light, also known as IPL, instead of the oven. And we'd also like to develop more recipes for other trace widths for other applications. We also plan to further test other aspects of the printed strain gauge, such as temperature drift, noise, and how reproducible are these values for each printed strain gauge. This work was supported by 2 National Science Foundation awards, the first one being part of the National Nanotechnology Coordinated Infrastructure, NNCI, and the second one being a part of the MRI Nexus project. If you'd like to know more, you can check out some of these references. And with that, thank you very much for listening.